So this is the required practical on acceleration. So here you can see the equipment that we used in class. What we've got is a glider on an air track with card on it. And then the card goes through something called light gates. And these light gates measure the acceleration. What we do is we add different weights to this string to get it to accelerate at different rates. Okay. And that is the experiment. So let's go into it in more detail. So what we've got on here is a weight or weight stack attached to a pulley. Okay, this reduces the friction between the string and the table because we want to measure the acceleration of that glider there, and we don't want the friction to affect the result. We've got light gates which measure our acceleration. We've got an air track again to reduce the friction between the glider and the track itself. And there's the glider. The card is important because that's what the light gates read. It's important we know what the card width is and then put that into our light gate software. Right, so again, here it is. Let's go through and write a quick method. So set up a glider on an air track with a string attached to it, which we've done. Place 5 10 Newton masses on the glider. This is important because what we want is to add weights to the stack to see how that affects the acceleration as it pulls it. But we must keep the mass of the entire system, so everything on there exactly the same. So all we do to keep the weight the same the whole time is take the weights from the glider and put them there. That means the weight of everything remains constant, which is an important control variable. Take a mass from the glider and attach to the end of the string and hang the mass off the edge of the table, which we've done. Use a pulley to reduce the friction between the table and the string, which we've got there, and allow the masses to pull the glider. So we let go of the masses, they pull the glider. Use the light gates to measure the acceleration and write it down. Now all you do is repeat steps 3 to 6 until there are no masses on the glider and all are on the end of the string. So what we do is effectively we're increasing the weight here, increasing the force on the glider, so we'd expect it to accelerate. So let's have a look at why we're doing certain things. So set up the air track and vacuum cleaner on blow. So the air track and vacuum will reduce the effect of friction on the glider, so it's only the weights that are affecting it. Measure the distance of the card and input into light gate software. To ensure the light gate software can accurately measure the velocity at each light gate. So as a result, the light gate software needs to know the length of the card so it can work out the speed, because speed is distance divided by time, and the length of the card is the distance. Calculate acceleration with 1 Newton of force added to the weight stack. Repeat 3 times. To give the first set of results and allow a mean to be calculated. Remove some weight from the stack and place on the glider and repeat the practical. This is to ensure the mass of the entire system stays constant and give further results for a varied force. All right, so that's a control, we want to keep it the same. And repeat the above step 3 more times, removing 0.2 newtons each time. We do that to vary the force further and give at least 5 sets of data. That's important to show a trend. Here's some example data. So you can see as we start to increase the force on the glider, our acceleration starts to increase, which is what you would expect. All right. Now, here are some examples of some questions. So it says, before attaching the mass holder, the student placed a trolley at the top of the runway. The trolley rolled down the runway without being pushed. So here's something very similar. Instead of got a glider on an air track, we've just got a toy car on a ramp. What change to the apparatus in the diagram could be made to prevent the trolley from starting to roll down the runway? So at the moment, that's going to roll down the runway, okay, and that's because it's on a slope. If we make the slope less steep, it might not roll down the runway anymore. To make it less steep, all we do is move the wooden block to the left, which is that one. The student attached the mass holder to the string. The string rubbed along the edge of the bench as the mass holder fell to the floor. It's just what the student could do to prevent the spring from rubbing. So they could put a pulley at the end of the table that reduces the friction between the table and the string. So use a pulley. Now, all we do is plot our results, choosing a suitable x-axis, okay, which is there. There's our scale, just there. Plot the results, which we've got here. It's clearly a straight line, so we draw a line of best fit. Describe the relationship between the resultant force on the trolley and the acceleration of the trolley. So because it's a straight line and passes through 0, 0, it's directly proportional. Now remember, you can also work out from the table, if you're not given the graph, whether it's directly proportional or not. And as long as the results are similar, we can say they're directly proportional. You can see these results are very similar when we do one of the readings divided by the other, or one factor divided by the other factor. We get roughly the same readings, which means it's directly proportional. The reason why they're not exactly the same is because of random errors in our experiment. If there were no errors, they'd all be exactly the same. Right. Describe how the investigation could be improved to reduce the effect of random errors. So these are standard answers. Repeat measurements, ignore anomalies, and calculate average. We just get our equation from here, and then we work it out like this. I'm not going to go through that because it's pretty straightforward. 2 students investigated how the acceleration of a trolley depends on the force applied to the trolley. Before starting the investigation, each student wrote a hypothesis. The acceleration of the trolley is directly proportional to the force applied. So that basically means if we do one thing, one factor changes, let's say it doubles, the other factor will double as well. Hypothesis B, changing the force applied to the trolley will change the acceleration of the trolley. Consider hypothesis of student A. Predict what would happen to the acceleration of the trolley if the force applied to the trolley is doubled. So if it's directly proportional, if the force applied is doubled, then the acceleration will double. Why is it difficult to make valid prediction using the hypothesis of student B? So the hypothesis does not say how increasing or decreasing the force increases or decreases the acceleration. That's why hypothesis B is not as good. Right. So write a list of any other equipment the student will need to complete the investigation. So we need some way of measuring the acceleration. We need some way of pulling it to measure the force. So we've got slotted masses, string and a pulley to pull it down the slope so we know how much force is pulling it. And then we need light gates and a Datey logger to measure that acceleration. Why should the student use a sloping runway? Basically, we want to use a sloping runway to reduce the effect of friction on the trolley. If it wasn't sloping, okay, friction would have more effect. The slope compensates for the friction. And this is just a method again. So all we do is do the following. We get our diagram ready to help us. Okay, so this is if there was no slope. So set up a trolley with a string attached to it and place on the table, which we've done there. Place 5 10-Newton masses on the trolley, which we've got there. Take a mass from the trolley and attach it to the end of the string and hang the mass off the edge of the table, which we can see there. Use a pulley to reduce the friction between the table and string, which we've done, and allow the masses to pull the trolley. As the trolley moves, it goes through the light gates, and that measures the acceleration. Repeat steps 3 to 6 until no masses are on the trolley and all are on the end of the string, measuring the acceleration each time, and that will give us a trend. So the students use the same trolley throughout the investigation to suggest why, so that the mass is constant. Remember, for a fair test, we've got to keep the mass constant. If we change the mass, that would affect the acceleration, and all we're wanting to look at is how force affects the acceleration, not the mass. Now, explain why, the students' results are shown as a graph in figure 2. Explain why hypothesis A gives a better explanation of the results. Okay, so you can say hypothesis A is correct because the results give a straight line that passes through the origin of 0, 0. As we know, a straight line passing through 0, 0 is directly proportional, and that's what the hypothesis A was. It showed that the acceleration of the trolley is directly proportional to the force. And that is it. Thank you very much.